Hi, good morning to everyone. It's for me a pleasure to be here in this 20th Total Reflection XY conference because I think that this number is a very beautiful number. 20 years, sorry, 20 conference imply 40 years of very hard work in this field. So okay, I need to be here. With the help of Aldona, yes, I'm here, not really in face to face because, okay, personal circumstance as the reasons, but yes, using this digital media. Okay. So thank you to Aldona for the invitation and to the organizing committee. And also the pointer. Okay, good. This small brief history of the technological and conceptual total reflection X-ray fluorescence evolution from the origins to now. It's a very difficult task, but okay, this was a very beautiful challenge for me. And okay, here it's my results. Um, I recommend, of course, Sever, the book of Reynold Clockenkamper and Alex Bombolen, because it's the first and the more important monographic reference for TXRF, and I always I like recommend. If we begin this historical travel, the first key moment was the discovery of the X-ray. If we have not X-ray, we have not nothing, any X-ray spectroscopy. So the discovery of X-ray in 1895 was, of course, the first and fundamental step for the development of all the X-ray spectroscopies along the time. So after of trying the X-ray, we need the use of this X-ray to the spectroscopical X-ray fluorescence application, and this was due mainly to Moseley in 1960. Because the relation that he found between the energy of each one of the X-ray lines transition and the atomic number for all the elements of the periodic table was fundamental to establish the qualitative correlation of the X-ray fluorescence spectroscopy and the analytical application of this technique. In fact, here you can see, I think that one of the first spectrometer of X-ray fluorescence in the history, this was used by Moseley in the experiments to obtain this quadratic relation. A very important step was the discovery of Coptron in 1923 of the existence of the total reflection of the X-ray on any material. This discovery was very, very important because allowed the use of the X-ray in a total reflection geometry. In this very early date, you can see the relation between the total reflection angle and the rho square of 2 times the scattering factor of the refraction index. Very beautiful. Coptron developed this relation, and it's a relation very useful for us today, as you well know. Okay. The next step, of course, if we now combine the X-ray with the spectroscopical application and the X-ray fluorescence phenomena with the fact that total reflection exists, John Eder and Oriuchi, you can see, in 1970 years, more than 50 years from the Compton discovery of the total reflection, applied the total reflection geometry to introduce in this interaction area a sample as a proof for elemental analysis. This idea was really the first step of the actual total reflection X-ray fluorescence. After, during the 2 decades, in 70 and 80 years along this year, mainly two groups, the groups of Vienna, by the world now for us, for all, Peter Bobrasek and Eginer, and the group of Germany by Schwenks and Knott and other, for example, Klockenkamper and also Alex von Bohlen, work very, very hard in the development of the theoretical concepts, the basics about the use of the total reflection in real sample, in analytical sample, and in real matrix, okay? And all in parallel in the development of instrumentation, operative instrumentation, which allow the use for the general public. For these works, they were distinguished with the Bunsen-Kirchhoff Prize in 1991, and the task was theoretical and instrumental development in total reflection X-ray fluorescence. So from this point, the first commercial instruments appears in the market, and these were due to the help and suggestion, scientific support of the Germany team, developed in collaboration with Richard Schaefer, the Extra 2 spectrometer. This, in fact, is our spectrometer that we bought in 1989. Yeah, the first instrument, TX-RF instrument in Spain, in any case, very much time ago. And in parallel, the group of Vienna developed the named as Bobrasek chamber. As you can see, this is a modern version of the chamber, but the more important is that the TX-RF technology through the International Atomic Energy Agency was distributed around the world for many countries, and was a technique. Okay, it's time more now around the world. Good. So if we now look the scientific outputs along the time up to now, we obtain this behavior. From my point of view, the modern total reflection X-ray fluorescence spectrometry birth in this year for me. Birth in 1980, 5 years really, when the first commercial instrument appears in the market, because you can see that from this point the increase of the scientific output was very, very, very high and very, very quick. Up to the year around 2000 year. From this year in advance, you can see that appears a saturation effect, where we obtain, you can see, an average output around 60 publication per year. In this stage, I want to do a small remark, because I think that is important, and is the impact that the enforced TXRF project, this cost action, had in the scientific output of the TXRF. In the 4 years, approximately 4 years of development of this project, the impact, the scientific output increase up to the top, up to now, of scientific publication, around 90 in this year, which was very, very important. But when the project finished, you can see how the number of publications go to the average, again, around the 60 publication by year. Okay, I think it's a suggestion for all you that, okay, think in a collaboration of this kind of collaborative works. It's very, very interesting, and it will be a very good proposal for any of yours. If we now evaluate the conceptual of the TXRF, the K concept, really, we need to think that before to the Bethnik et al. Works in 1989, the vision of the total reflection was a geometrical vision. The way of thinking was, okay, we have an excitation by the incident beam, and we have a second excitation by the reflected beam. So we have two excitation, an amplification of two. Okay. Beckley and in this pioneer work show that really we need to think in TXRF in a ondulatory way. That is, we have a electromagnetic wave that is totally refracted in the surface. So there is a region, a special region, where there is an interference between the incident and the reflected beam. This X-ray standing wave field, it's the result of a constructive interference. And in this constructive interference, the amplification of the intensity varies from 2 up to 4. So it's a different way, but really it's similar because both reasoning produce the same final results, which is curious, very curious. And this is the question. If we have this intensity distribution of the standing wave field, and we have a sample into this X-ray standing wave, we obtain this intensity distribution that increase in a factor 2 up to 4 from the out of the total reflection condition, depending of the geometry mainly of the sample of the deposition, in fact. Okay, but simultaneously, and this is the quantitative key for TXRF, we obtain a minimization, very strong minimization of the background intensity of the reflector signal. So we have the perfect combination from an analytical point of view and for any analytical instrumentation, that is, optimize the signal to noise ratio. Here we have an optimization of the signal and simultaneously a minimization of the noise, okay? Of the background in this case. So this is ideal, and this is really the quantitative key that gives to the TXRF all the analytical powerful. This is really the reason. And as I told we obtain what? Very, very low detection limits, picograms, fermigrams if we use high flux source, synchrotron, metal jet source. Okay, this is PPV or even PPT. Yes, this is very competitive with other techniques that are in competence with TXRF or TXRF with them. And of course, simultaneously, this techniques allows a very, very simple sample preparation. And this is one of the more powerful analytical keys that TXRF offer. Because the internal standard method, which imply the linear relation between the concentration and the intensity of each one of the elements deposited in over the surface of our reflector, imply that we can eliminate all the matrix effect, and we can use a simple standardization with a monoelemental for analyze its kind of sample. I won't share with you, this vision of the total reflection of the TXRF in a 3D dimension. The 3D dimension is the angle, the incidence angle. Here you can see that we have a series of X-ray TXRF spectra. You can see energy intensity is one of the lines, but are ordered by angle of incidence, and we obtain a real vision of what happened around of the total reflection angle. This is a very beautiful vision. More detailed, it's this case, for example, this is a ceramic particles, and we can see several effects. The silicon of the reflector, yes, here we are out of total reflection, we have high signal of silicon, but if we are going to total reflection angle, and okay, we are into total reflection, we have very low silicon of our reflector signal. But it's contrary, for example, for trace elements, calcium, titanium, in this case. If we are out, we cannot detect analytically, quantitatively the calcium or the titanium. It's very, 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 very small. But in total reflection angle, we can see the improvement of the signal. Yeah, we are working in total reflection, and the more spectacular is for iron in this case, because here there is a very, very beautiful amplification of this stationary wave, standing wave. Similar for rubidium, and okay, in the same way that for silicon, for copper and Raleigh, it's only a present, because I think that this vision of total reflection is very beautiful, and allow us to think what happened when we are analyzing in a more complex way. Now, if we speak about technological improvements, we have different parts that are important. The development of the X-ray source, the development of the optics, and of course, the development of the detectors. And has been very, very, very important. If we begin with the X-ray source improvement, the sealed metal ceramic tubes are the origins. When I begin to working with X-ray for diffraction and for initial fluorescence, the first tubes, X-ray tubes, were of this kind of shell tube. Really, these tubes are very similar. Conceptual is the same that the Röntgen X-ray tube. Filament excites electrons, accelerate. There is Bestron in a cathode, and we generate an X-ray beam that is used. In this case, we obtain brightness, photon density in the order of a power 4, 6. It's fine for fluorescence and diffraction experiment, but the best is increase the brightness to obtain lower, for example, the detection limit in total refraction in TXRF. Then the second step was the development of the rotatory anodes, which use the principle of the same, because there is a filament that it's accelerating electrons, but in this case, not in a static anode, but just in a rotatory anode. This disk it's rotating at very high velocity, and then the density of electrons can be higher. You can see in the order of two factors. No, not 2 factors. Sorry. 2 exponential order from 6 up to 8. Okay, this is a very high increment due to the use of the rotation and the increase of the electron of the emission of the filament. There is very much electron. Okay, good. I remember the way of these systems, very big high voltage transformer. It is, for example, it's relatively new, and the weight is only around 80 kilograms. But I remember that the first instrument that we work, the weight was around 250 only. The X-ray transformers. So wow, very big, very weight, difficult of work of translate from one lab to other lab. That's okay. But okay, now the source are smaller and with a brightness very high. For example, the microfocus technology next to the field emission source. Here you can see the cross-section of reflection microsource and the cross-section of a transmission microsource. And here you can see the cross-section too of a field emission microsource, which is really very similar to the transmission, but here use carbon nanotube as emitter. So there is a quantum effect which allowed increase the number of electrons that impact over the target. So with this, we increase the density of photons in a very high quantity. As big as a power 7 up to 10. It's a very big intensity. These commercials shows microsource, and this use the reflection microstructure, and this use the transmission microstructure. But there is more high brightness, the metal jet source that are okay as a small synchrotron, because in this case, in concept is the same that rotatory anode, but change the disk of the rotatory anode by a metal jet. In this metal jet that is continuously running. Yeah. So we can apply a very high electron density and then obtain a very high photon emission. For this reason, we obtain a power between 9 and 11, really. Okay, 10, 11, very near of the 11, which is a very, very high brightness to apply in laboratory application, because this is for laboratory applications. The problem is it's very expensive. This is the more serious question. And of course, we have the hybridness synchrotron source if we really need very, very high flows, photon flows. From power 12 up to power 20, 22, and even 26 if we consider the X-FEL, the free electron laser. Yes, it's possible now. So all kind of experiments can be designed and can be applied in this installation, okay? From the optic improvements, the difference is substantial from the initial system. This, for example, used the total reflection principle theory to use different angle of incidence cut off to generate a low pass filter, because depending on the angle that the flows of the Schultz incident, in this case over this quartz disk, we obtain eliminate the energies higher than 40, higher than 20, or higher than 10 kiloelectron volts. So we obtain bands of energy for excitation of all samples. Today, the things it's different, very different is this. We use multi-layer with generated with very sophisticated channels with resolution of atomic resolution. So it's very beautiful in curved. It's really all science today. But the more important is that it's possible to adapt the optics to the range of energy in an easy way today. It's really very easy. For example, this system was the system of the Atomica, where with the same X-ray tube and alloy of molybdenum and tungsten, we can, and in this case a double multi-layer, we can optimize the energy of excitation to the L beta, tungsten L beta excitation in this condition. In this condition, we can obtain excitate the same sample with molybdenum GLF, and in this geometry excitate the same sample with Westerland of tungsten. So this is very, very, very interesting, because allow a dynamic way of analyze. Good. From the detector, wow, it's very, very important. The initial have not resolution, very poor resolution, and very down cone rate, the Geiger. For X-ray fluorescence as not very good. Yes, for diffraction. This is similar. This is not very good for fluorescence, but yes, the silly detector, where the resolution was very good. And during all the development of the first instruments was the detector mainly used, because the resolution was very good, and the maximum current rate was also adequate, and also the energy range. And today we are here. We are with silicon drift detector, because I love very, very beautiful characteristic from 125 up to 150 electron volts. It's totally enough to evaluate correctly any energy this energy dispersion spectra for the TX-RF. Okay, so it's good. It's the time. Thank you very much for your patience, and again, thank you for your patience. And I hope to see you in a future meeting face to face if it's possible. I think that is the best. Okay, see you.